Okay, so in section 12.1, we're going to talk about the goodness of fit test. So before I actually get into the material, I want to talk about what we're checking for. So let's think of something where there's going to be proportions for multiple categories. So maybe we're talking about the colors of M&Ms, the distribution of colors of M&Ms, or the distribution of age brackets in a school, things like that. So whenever information is gathered about this, we have an expected distribution for these age brackets or these colors. And what we're going to do is learn how to do a test to figure out if that distribution is indeed a good fit. So let's talk about some of the characteristics of the chi-square distribution. So it's the chi-square distribution that we're going to be using for the goodness of fit test. So the first thing to take note of is it's not symmetric. The shape of the chi-square distribution depends on the degrees of freedom, just like the student's t distribution. And as the number of degrees of freedom increase, the chi-square distribution becomes more nearly symmetric, and the values of chi-squared are non-negative, greater than or equal to 0. But if you think about it, anytime you're squaring something, it's going to become positive. So here's an idea of what's happening with chi-square, going from 2 degrees of freedom to 30 degrees of freedom. And with 2 degrees of freedom, it's quite a strange looking graph. And then with 30 degrees of freedom, it's starting to become a little bit more symmetric. The goodness of fit tests are used to test hypotheses regarding the distribution of a variable based on a single population. So the goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. So first, let's talk about expected counts. Before I do that, I want us to think about a bag of M&Ms. If I tell you that there are 20% yellow M&Ms and that I have a bag of 50 M&Ms, then you would expect to find 10 yellow M&Ms in that bag. And we would find that because we would take that 0.2, so that the 20% yellow M&Ms, so that 0.2, and multiply times 50 to figure out that we're expecting 10 yellow M&Ms. That's what these expected counts are. So suppose there are n independent trials of an experiment with k being greater than or equal to 3, mutually exclusive possible outcomes. Now I want to point out k is talking about categories. So in reference to M&Ms, that could be like yellow and green and blue. So at least 3 different categories, and they have to be mutually exclusive, so you can't be blue and green at the same time, at least not if you're an M&M. And same with age brackets. You couldn't fall into more than one age bracket. And it says let P1 represent the probability of observing the first outcome, and E1 represent the expected count of the first outcome. P2 represents the probability of observing the second outcome, and E2 represents the expected count, and so on and so forth. So what they're saying is they're taking these categories and taking their probability for each category, so for yellow, blue, green, etc., and that's going to be P1, P2, P3, and so on and so forth. And then once they figure out the expected count, so just the probability times the number of M&Ms total, that's going to give us the expected count for our red and blue and green, so on and so forth. All right, so let's talk about the test statistic for the goodness of fit tests. Now, this is one of the times that I will warn you, the Casio is going to be a little bit harder for us to go through. It's going to take a little bit longer. But again, it was $100 cheaper. So this is the price we finally have to pay for using the Casio. So the test statistic for the goodness of fit tests, let O sub I represent the observed counts of category I, E sub I represent the expected counts of category I, K represent the number of categories, and N represent the number of independent trials of an experiment. Then the formula, chi-squared, equals the sum of the observed value minus the expected value squared over the expected value. And we're going to do this for all the categories, so running from 1 through k. Also, make a note here that your chi-squared distribution has k minus 1 degrees of freedom. So again, the k minus 1, k is the number of categories. So the degrees of freedom for chi-squared are going to be the number of categories minus 1. And then just to simplify this, so chi-squared is going to be the sum of the observed minus the expected count. That'll be squared over the expected count. And we'll do that for all categories. So we're going to walk through the process. We're going to use the classical approach. So when we get to step 3, we're going to go with the classical approach. And this is going to feel relatively similar to 10.3. So for step 1, we're going to determine the null and alternative hypotheses. Well, these are pretty easy. The null hypothesis is just that the random variable follows a certain distribution. So this is typically like what would be advertised for the proportion of colors, or what a school currently thinks their age distribution is, things like that. And then H1, so the alternative hypothesis, is that the random variable does not follow the distribution in the null hypothesis. I do want to make a point here that we can only determine if it follows a distribution or if it doesn't follow a distribution. So if we have M&Ms and we think that there should be 20% of every color, and whenever we go through our bag of M&Ms is all yellow, we cannot make the conclusion that there were too many yellow M&Ms. We would just be concluding that it didn't meet the expected distribution. Our second step is going to be to decide on a level of significance, alpha, depending on the seriousness of making a type 1 error. And again, alpha is going to be given to us whenever we're doing this. For step 3, we're going to calculate the expected counts, so E sub I, so the expected counts, for each of the categories, so K categories. And again, E sub 1, so the expected count is just going to be the N times the probability for that category. And that's going to be, we're going to go do that for all categories, and N is the number of trials. We also need to verify that the requirements for the goodness of fit test are satisfied. So to do that, we have to make sure that all expected counts are greater than or equal to 1. So whenever we do N times P, it has to be greater than or equal to 1. And no more than 20% of the expected counts are less than 5. So this is 20% of K. So no more than 20% of the expected counts are less than 5. And again, we're going to go through and use the classical approach. So we're going to be computing chi-squared. So this will be our test statistic. So our chi-naught squared. All right, and then for step 4, this is where it's going to start to feel like what we were already doing with our previous hypothesis tests. So we're going to determine the critical value, and we'll be looking up the critical value just like we did whenever we were doing hypothesis tests on the mean of a population. And then the goodness of fit tests are all going to be right-tailed tests. So the critical value is that chi sub alpha squared with k minus 1 degrees of freedom. And then essentially, if our test statistic falls into this critical region, we're going to reject the null hypothesis. And if it doesn't, then we're going to fail to reject the null hypothesis. Remember, if we fail to reject the null hypothesis, then we cannot conclude that the distribution is different. And if we do reject the null hypothesis, then we would say that there is enough evidence to conclude that the distribution is different. All right, let's actually start going through this. So again, this is just a reminder of how we're going to find our chi-squared. So how we would work to get our test statistic. If you have a TI-84, this is where you do get a little bit luckier. So you can go through these steps if you're using a TI-84 Plus. I'm going to go through the steps using a Casio. So for number 11, plain M&Ms. According to the manufacturer of M&Ms, 13% of the plain M&Ms in a bag should be brown, 14% yellow, 13% red, 24% blue, 20% orange, and 16% green. A student randomly selects a bag of plain M&Ms. He counts the number of M&Ms that were each color and obtained the results shown in the table. Test whether plain M&Ms follow the distribution stated by the M&M Mars Company at alpha equals 0.05 level of significance. Well, this table is giving us our O sub I, our observed count. So this is our O. We need to calculate our expected count. So for our expected, that's going to be our E sub I. We're going to take the proportion or the percentage for each color. So we had 13% brown, 14% yellow, 13% red, 24% blue, 20% orange, 16% green. And we're going to multiply that by N. N is going to be the total number of M&Ms, which in this case is 400. So we're going to do 13 times 400 and get 52. 14 times 400 and get 56. And again, 13 times 400, get 52. 24 times 400, 96. 20 times 400, and we're going to get 80. 16 times 400, and we're going to get 64. So these are the expected counts. So to figure out our chi-squared, we're going to do the sum of the observed minus the expected squared over the expected. And we're going to do this for each category. So we're going to have 61 minus 52 squared over 52 plus 64 minus 56 squared over 56 plus 54 minus 52 squared over, and now we're going to work all of those out and add it up. And because the Casio won't necessarily hold all of this in, I'm going to do each one individually. Alright, so working each of these out, I've gotten a decimal approximation. Then I'm just going to add all this up. And we're going to get 18.738. So this is our test statistic. We need to have our nice little picture of chi-squared. And we need to find our critical value. So to do that, we're going to use our chi-squared table. So we're going to use a level of significance of 0.05, and then our degrees of freedom is going to be the number of categories minus 1. So there's 6 colors, so 6 categories. So we're going to have 5 degrees of freedom. So alpha is going to be that 0.05, and our degrees of freedom is going to be 5. So here we have our chi-squared distribution. We have alpha of 0.05, and again, this is letting us know this is the area to the right of the critical value. And we have 5 degrees of freedom. So we're getting 11.070. So this is going to be 11.070. Our test statistic came in at 18 and change, so 18.738, which is in our critical region. So we are going to reject H naught. So there is sufficient evidence to conclude that the distribution is different. One thing I do want to mention that we didn't specifically double check and should have is that our expected counts, that all of these expected counts were greater than or equal to 1, and that we did not have more than 20% that were 5 or less. So, because all of these were over 5, we didn't have anything to worry about. All right, let's look at number 21. So, pedestrian deaths. A researcher wants to determine whether pedestrian deaths were uniformly distributed over the days of the week. She randomly selects 300 pedestrian deaths recorded the day of the week on which the death occurred and obtained the following results. The data are based on information obtained from the Insurance Institute for Highway Safety. So it wants us to test the belief that the day of the week on which a fatality happens involving a pedestrian occurs with equal frequency at the alpha equals 0.05 level of significance. So we're going to actually write out our hypotheses. So for our H naught, we're going to say that the distribution is the same on all days of the week. So our H1, our alternative hypothesis, is that they are not. All right, so let's start this one with our picture. So our chi-squared distribution looks something like this. And it tells us that we're going to have alpha of 0.05, and we need to find that critical value. Well, we know the alpha is 0.05. The degrees of freedom is going to be k minus 1, or the number of categories minus 1. There's 7 days in a week, so 6 degrees of freedom. So 0.05 with 6 degrees of freedom is going to give us 12.592. So 12.592. All right, now let's start the process of working on our test statistic. So I'm going to actually rewrite this information. So we start with Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and then Saturday. And our observed counts are those listed. So our expected counts, we think that there is an even distribution, or we're testing to see if there's an even distribution on all days of the week. So of our 300 deaths, we would expect them to be evenly distributed. So we would take that 300 and multiply times 1/7, so the probability of 1/7, which is going to give us 42.86. So this is going to be the same for every single one, so 42.86. Because these are all the same, we can go ahead and talk about making sure that all of our expected values are greater than or equal to 1, which they are, and that there's no more than 20% that are 5 or less. And again, since these are all 42.86, then indeed we're going to meet those requirements. From here, we're going to work on making doing our test statistic. So again, it's going to be observed value minus the expected value, and then square that and divide by the expected value. So we're going to have that for the observed value. So 39 minus 42.86 all squared over 42.86 plus 40 minus 42.86 squared over the 42.86. And we're going to do this for all days of the week. This is going to give us about 13.147. So this is our test statistic. So this is our chi-squared test statistic of 13.147. So we're going to come back up here. Indeed, we're going to be over here in that critical region. So that 13.147. So we are going to reject the null and conclude so we're going to reject H naught and determine that there is sufficient evidence to conclude pedestrian deaths are not evenly distributed across the days of the week.